Hi guys, in this video we will be looking at the qualitative analysis test for gases. Now we have different gases that we can test for, and these include ammonia, carbon dioxide, chlorine, hydrogen, oxygen and sulfur dioxide. In our test for cations, we had the production of ammonia gas which we tested for with a damp red litmus. In a test for anions, we had the production of ammonia in the test for nitrate ions, in which ammonia gas turned damp red litmus blue, and we had a test for sulfur dioxide in testing for sulfite ions, in which the sulfur dioxide turned potassium manganate 7 from purple to colorless. So we have already looked at the test for ammonia and sulfur dioxide. Also, when testing for carbonate ions in anions, we had production of carbon dioxide gas which turned lime water milky. So out of the six gases that we need to test, three have been mentioned in the previous test for cations and anions. We will be looking at these tests again along with tests for identification of the chlorine gas, the hydrogen gas and the oxygen gas. The first gas we will be testing for is carbon dioxide. So carbon dioxide is produced when a strong acid is added to either solid carbonate salt or a solution of an aqueous carbonate. Here in this diagram, we have a solid carbonate salt present inside a test tube to which we are adding HCl. And when we add HCl, if you can see in the middle diagram, there are a few bubbles forming. This is called effervescence, and these are bubbles of CO2 gas. Now we have placed a delivery tube into a test tube containing lime water, and the other end of the delivery tube is placed inside the test tube in which the carbon dioxide gas is produced. So this will transfer carbon dioxide from the reacting test tube into the test tube containing lime water. So what will happen? This carbon dioxide will move into the test tube containing lime water. Lime water is calcium hydroxide solution. So when it moves into the test tube containing calcium hydroxide solution, which is known as lime water, this lime water starts turning white or milky, as you can see in the last diagram. So this white color is due to the formation of calcium carbonate, which is insoluble in water. So this is the theory behind testing for carbon dioxide. So as a result, as an observation, we write effervescence and a colorless gas evolves, which turns lime water milky. However, this test is practically rarely performed because when we have a solid in which acids react to effervesce and produce CO2, or we have a solution in which effervescence is occurring, it is definitely due to the presence of carbonate ions. So we are certain without testing for the gas that the gas evolved is carbon dioxide. However, we still do write the test in our observation column, which is effervescence and the colorless gas evolves, which turns lime water milky. The next gas we are testing for is sulfur dioxide. And sulfur dioxide can be produced by looking at the reaction shown on the in the diagram on the right. We have a mixture of sodium sulfite. Sodium sulfite is Na2SO3. This is sodium sulfite. And HCl. So this would react with 2 moles of HCl. Why 2 moles? Because there are 2 moles of sodium ions present. And it is warmed over a Bunsen burner. When you warm this, this results in the production of SO2 gas. It forms H2O and it forms NaCl, 2 moles of NaCl. So these are the products formed when this reaction occurs. Now, this sulfur dioxide gas, which is liberated, when it touches the damp damp paper which has acidified potassium magnet absorbed onto it, it converts it into a colorless solution, or rather the paper turns colorless, the purple color discharges. We can test this better by adding the KMnO4 into the test tube in which the reaction is taking place. When you add it, it is purple. As soon as the reaction proceeds, it turns colorless. So this is what is meant by turning from purple to colorless. And change of potassium manganate from purple to colorless represents oxidation, which means the sulfur dioxide gas in the case of the diagram on the right has been oxidized. In the case of the diagram on the left, even the sulfite ions will be oxidized to sulfate. So this way, if we add it to the solution, we are not testing for the gas. But when we use the potassium dichromate paper, we are actually testing for the gas, and the gas gets oxidized when it is absorbed onto the potassium dichromate paper, hence turning it from purple to colorless. Continuing with test for gases, now we have test for ammonia. Ammonia, when liberated, turns damp red litmus blue, as seen in the diagram. The good thing about this diagram is the color that they have shown for the red part of the litmus paper and the blue part of the litmus paper is very much accurate. If you use a good litmus paper, these are the observations that you will get. So we have a test solution and we have a Bunsen burner. So the test solution could be, there are two possibilities. This could be nitrate ions in which you add sodium hydroxide and aluminum foil and heat. This would result in the production of NH3, or there is another possibility. You could have ammonium ions in solution to which you add NaOH and heat. And in this case also you would end up with the same NH3 being liberated, and ammonia turns litmus blue because ammonia is basic in nature and litmus paper appears blue in a basic solution. So this is the test for the presence of ammonia. Continuing with the test of gases, we are going to test for chlorine now. Now, when chlorine gas is evolved, it turns the red litmus paper colorless, or it bleaches the red litmus paper. So the effect here is chlorine bleaches the litmus paper present. It takes away the color that is present. And it does the same thing with the blue litmus paper. But what is not shown here in the diagram is that when chlorine evolves, it turns blue litmus red and then it bleaches it. This shows that when it dissolves in the water present on the litmus paper, it forms HCl, and HCl being acidic turns blue litmus red, and chlorine is a bleaching agent as well, so it will bleach the red litmus paper and turn it colorless. So here, when we have the red litmus paper will not change color because ammonia is an acidic gas, right? It will dissolve in water forming HCl. The litmus is already red, and litmus is red in the presence of acid. So there will be no change of color observed. But using a blue litmus, when HCl forms, it will turn the blue litmus red, and then chlorine will bleach the red litmus paper and turn it colorless. So this is how you test for the presence of ammonia gas, chlorine gas, sorry. Test for the presence of chlorine gas. The next test is for hydrogen gas. And in order to remember how we test for hydrogen gas, just remember, pop goes the splinter, right? What is happening here? When we have production of hydrogen gas, usually how do we produce hydrogen gas? We add a reactive metal, not very reactive, right? Like in this case, we can add magnesium or we can add zinc, right? We add a reactive metal to a solution of a strong acid, H2SO4 or HCl. So you will see bubbles forming because these bubbles are hydrogen gas that is being produced. And when this hydrogen gas comes into contact with a burning splint is a piece of thin wood that is set on fire. When it comes in contact with that fire, it pops. What happens when it pops? Basically, hydrogen is a flammable gas. In the presence of oxygen in the atmosphere, it burns, and when it burns, energy is given off. And because this happens, and some of the oxygen that was there in the environment is pushed away from it, right? The splint or the other gas, and not only oxygen, we will say the air that is pushed away. This air actually extinguishes the flame that is there, and because hydrogen burns in this flame, we can hear a pop sound. This pop sound indicates that energy has been given off. This pop sound can be a very small pop or a very loud pop, depending on how much hydrogen gas is produced. So pop goes the splinter is how we test for the presence of hydrogen. The last gas we are testing for is oxygen. Now, oxygen is not a flammable gas. However, oxygen is needed to keep a flame lit. So this is the exact principle we are going to use in testing for oxygen. So how do you test for oxygen? Normally, you have nitrate that decomposes easily. So an example of such a nitrate is zinc nitrate. So when zinc nitrate solid is heated in a container, it will decompose to produce zinc oxide, NO2 gas, and O2 gas. Now we are going to be testing for the O2 gas that is produced, right? So when oxygen gas is being produced, we introduce a glowing splint. Now, how do you have a glowing splint? You put a piece of wood, small wood, on fire, and then you blow at it to extinguish the flame. Because the flame extinguishes, but the wood is still burning, it glows. This is what is known as a glowing splint. Now, when you introduce a glowing splint inside the container where oxygen is being produced, the oxygen is required for the flame to burn. So when it is exposed to oxygen, the flame relights. So the glowing splint is turned into a burning splint. And this shows that oxygen gas is present because burning of a flame requires the presence of oxygen. And because oxygen is produced in this decomposition reaction, the glowing splint turns into a burning splint. And then you can confirm that oxygen gas has been produced in this reaction.